Okay, good afternoon, everyone. Welcome to this colloquium. Our speaker today is Dr. Johannes from the Naval Research Lab. She got her bachelor's degree in physics from Mount Holyoke College in 1993, and then spent some time coaching volleyball and instructing physics labs before starting her PhD at the University of California in Davis in computational physics. After that, she started a postdoctoral fellowship at the Naval Research Lab, and then stayed on as a staff member in 2005. And currently, she's leading the Center for Computational Materials Science, also at the Naval Research Lab. She has got a few awards, among others, the Sigma Chi Young Investigator Award, and she's a fellow of the American Physical Society. And today, she will tell us more about how materials physics really drive the electrochemical performance of lithium-ion batteries.
Thank you very much. So thank you very much for the invitation, and for everyone who spent time with me today. It's really lovely to be here. I hope that everyone will feel comfortable, since this is kind of a small setting, interrupting me if I say something confusing or if you get lost or you want me to go back. I'd rather do that during the talk than have you all fall asleep because you're bored and got lost. All right, so let me just really quickly thank my collaborators. These are the people who are still with me at the Naval Research Laboratory. This is my computational colleague, Noam. Corey, Karen, and Sharka are all experimentalists who help make the materials that I'm studying. Also, I learned a lot about the battery field from John Goodenough, who many of you know invented the batteries that are in all of our things right now. He's actually a lovely person who, it's shameful, has not gotten the Nobel Prize in Chemistry. If any people out there are on the board, shame on you. And these are other collaborators who are not at NRL, but who worked with me on this, also experimental people. All right, so this is apparently not going to work. Okay. So, introduction to, it's not going to work because I didn't plug it in. Introduction to how lithium-ion batteries work. Many of you already know this, but for those of you who are maybe in other areas of physics, a lithium-ion battery in particular has three parts: a cathode, an anode, and an electrolyte. The lithium ions in the anode move through the electrolyte and into the cathode, but because the electrolyte has a wide electronic band gap, the electrons must pass through the load. For this to happen efficiently, you have to be able to store a large amount of lithium per unit weight on both sides, anode and cathode. If you can only get in 1 lithium per every 10 pounds of other material, obviously your phone is going to be heavier than you would like. We call this capacity. Also, if you get a lot of lithium in, but you can't get it back out or back in again, your battery is going to run at a very low rate or not at all. So that lithium needs to be able to move in and out of the cathode, the anode, and through the electrolyte easily. That is called, unsurprisingly, ionic mobility. And then the electrons also must be able to move. So you might imagine that since the electrons are just going around here through this conductive wire, that your materials would not need to conduct electricity, but they do, because these are macroscopic chunks of material in here. Once the ion goes out this way, the electron has to get over to the current collector. So we would like these also to be able to conduct electrons. That we just call conductivity. Okay, we'd also like the voltage between the electrodes to be as high as possible. This will give your battery a lot of power. They shouldn't really be much higher than 4.5 volts, because the breakdown voltage of the electrolyte is about 5 volts with state-of-the-art electrodes. This goes by the name power. We'd also like our electrode materials to be cheap and environmentally benign. This is becoming a really long laundry list of things we want from our materials. So what have we settled for? Well, not perfect in all of these categories for sure, but what we're using right now in almost all of our portable devices is lithium cobaltate on the cathode side, and a lithium intercalated graphite on the anode side. What are the downfalls of these materials? Well, you can only pull out 1/2 of the lithium per every cobalt ion before the material breaks down. So that's actually not terribly efficient. And you can only put in 1 lithium per every 6 carbon atoms on the graphite side. So we would like to be able to get more lithium in and out of both of these sides. In addition, cobalt is not exactly environmentally benign. It's not great if it gets near your groundwater. We're not great at recycling things, so we'd like to replace that with something better. But what is driving research in batteries, as is driving much research, is actually money. So this is the 3D elements that we generally use for redox couples, and they are colored and numbered by price in US dollars per kilogram. And you can see that cobalt has hit the sweet spot of being by far the most expensive one. So we'd like to replace cobalt also for monetary reasons, and that is actually why battery companies are trying to improve these materials.
A question, where's
Yep.
cobalt come from?
So that's a great question. I actually have a chart not in this talk that shows which materials come from where and whether we have political scarcity or actual scarcity. And I think with cobalt, so I'm going to say this out loud, but I could be totally wrong, and someone correct me if you know better. It comes from somewhere in Africa, and I'm not entirely sure where that is. But that's not perfect from our point of view, obviously. So that would also be another reason to switch it out. All right, so the method that I use to study these materials is density functional theory. I don't want to go into it deeply because most people in here aren't doing it, but I want to show you sort of how it works. It's material specific in that we don't put in ad hoc parameters into this. What we do put in is the constituent elements of the materials we're interested in. This I just drew a very complicated crystal structure that we could conceivably study. Actually, we only have to put them in as the approximate structure. We put them where we think they are, and then we can relax them to their actual ground state structure. And then we feed that, just the constituent atoms and their approximate structure, into a black box called DFT. And what this does is solve a mean field Schrodinger's equation. So it's atomistic in that it's solving them for the atoms, and quantum mechanical in that it's solving the Schrodinger's equation for the electrons. What we get out of that, then, is predictably what you get out of the Schrodinger's equation, which are wave functions, which you can square to get the charge density. You get the total ground state energy, the electronic structure or band structure, stress, strain, pressure, lattice constant, magnetic ground state. Anything that's the ground state of the material, you can get out of this. And then from these sort of basic quantities, you can derive things that are important for battery materials, such as voltage, the chemical stability, the phase stability, the ionic conductivity, electronic conductivity, and safety parameters. And I'll go into most of these in a little bit more detail. So if density functional theory has the requisite accuracy, and I will argue that it does in many cases, we could replace expensive synthesis and testing in the lab with density functional theory at a computer. This is the phrase that I put into all of my proposals. Program managers like this idea very much. What I like even more is that we can look at these battery materials and actually understand the sort of fundamental materials physics and chemistry that's going on there, because I find that very interesting. Okay. The primary thing that we think about with batteries is what's the voltage. Our batteries are even named after voltages, right? We have 8 volts and 12 volts and 6 volts and things like that. So can we calculate that voltage? Yes, we can. It comes from 2 different places in lithium-ion batteries. The first is structural. So how does the material actually change as you put lithium ions in and out? And you can imagine in a material where you could get lots of lithium ions in, which would be the ideal material, you might get lots of expansion and contraction as it goes in and out, and you might pay quite an energy penalty for that movement of the lattice. The other part is electronic. So I'm pulling lithium ions in and out of the material, but I'm also moving an electron from one material to another. And that electron has to sit in one energy state in one material and a different energy state in the other material. And that has a profound effect on the voltage, as I'll show you. In reality, these two cannot be decoupled. The charge of your system and the structure of your system are in most cases related. All right, but if we are to calculate the electronic voltage, or the voltage, this is the way we do it. This is the chemical potential of the lithium when there are X lithiums in the system, minus the chemical potential of lithium metal, which is always our counterelectrode when we're calculating voltages, divided by electron. And that gives you the Gibbs free energy. And voltage is simply the change in the Gibbs free energy over the difference in amount of lithium times the Faraday constant. These are all actually very simple thermodynamic equations. And then we have the thermodynamic equation for Gibbs free energy, which is that it's the change in internal energy. This is sometimes written as U per pressure times delta voltage, and temperature times delta entropy. Luckily for us, pressure is so small, I mean, we're just at atmospheric pressure, that term is tiny. And in fact, the entropy term is at least 2 orders of magnitude smaller in general than the change in the internal energy, which is the primary term. Also in density functional theory, we are sitting at t equals 0. So even if this term weren't happily small, we would have to pretend it was. So finally, if I want to calculate the average voltage of a material versus just lithium metal, I calculate the change in the internal energy divided by the change in the lithium content times Faraday's constant. And the change in the internal energy is exactly one of the things that I told you falls out of density functional theory. So this is actually a very easy, straightforward calculation for us. And here's an example. Let's say I wanted to calculate the voltage of lithium cobaltate if I could pull out all of the lithium, which I previously told you you can't. I calculate the total energy of lithium cobaltate minus the total energy of cobaltate without lithium, subtract off the energy of one lithium ion in its metallic state, and divide by 1 minus 0. And this gives you, if you use the correct methodology, excellent agreement with experiment. Okay, once we've done this, and we can show that we get excellent agreement with experiment for a wide range of materials and their measured voltages, we can go back and look at what determines, from a materials physics point of view, where that voltage is coming from, and therefore maybe how we can change materials to make the voltage higher or lower or different as we like. And as I mentioned, it's really the change in the state of the electron that determines the voltage. So imagine the highest occupied state of the anode is right here, and that's where your electron sits before you discharge your battery. That electron has to go over into the cathode, where it's going to be sitting in a D state. So almost all cathodes are transition metal oxides, and their valence bands are made of D states. So that's why I've labeled this as D states. And the difference in energy that that electron experiences when going from one material electron state to another, I'm calling delta E here. It's directly related to the voltage. You have to multiply it by some things to get the voltage, but it's very much related. So now imagine I have a different material, and for some reason the D states of that material sit higher in energy. Then the electron gets less of a gain in energy. When it drops over, the delta E is less and the voltage is less. So the point of this slide is just to tell you the higher the D states are in your cathode material, the lower your voltage is going to be. And this is just a general principle by which you can understand which materials might have better voltages than others. Okay, but what determines the height of the D states? Well, 2 things, the bonding and the Z, or the atomic weight. So as I move from left to right across the periodic table, my elements get heavier, I get more core charge, and the D states are bound more tightly. That lowers their energy. So you can assume that as you move from left to right across the periodic table, your D states will move down, they'll be more tightly bound, and your voltage will move up. Also, in these transition metal oxides, you have oxygen P states and transition metal D states. These bond and anti-bond with one another. That pushes the D states up, and you get these hybridized transition metal oxygen states here and hybridized oxygen transition metal states here. These are the actual states you're going into. So you have 2 things together that work to determine this height. How heavy is your transition metal, and how strongly bonded is it with the oxygen? Okay. Now, transition metal oxygen bonding is not straightforward. They don't just bond and anti-bond like I showed you. D states have an orbital shape. The orbitals, like this one, which is Z squared, that point directly at the surrounding octahedra, these are nearly always octahedrally coordinated. If these lobes point directly at the oxygen, such as the Z squared and the X squared minus Y squared ones do, then you get very strong bonding and anti-bonding, because there's lots of overlap between the oxygen states and these lobes. These go by the name EG. There's 2 of them, and they're strong anti-bonding states. All right, but there's 3 other D states. They have these shapes, and those point away from the oxygen, and therefore they bond much more weakly. These are the weak anti-bonding states. The splitting between these 2 states in transition metal oxides can be greater than 1 eV. And if you know what the approximate voltage is of your batteries, it's about 4.2 or 4.3. 1 EV can make a huge difference on that. So if I'm pushing up states by 1 EV, I'm decreasing my voltage by 1 EV. So this is something we want to steer around or exploit, as the case may be. All right, so I've just shown you how the bonding goes in these materials, and this is an example of calculations and experiment for different, this is the structure of lithium cobaltate, but with different transition metals subbed in for the cobalt. And what you can see is, as mentioned before, as you move rightward across the periodic table, the voltage goes up. All right, and in some cases, this structure is not stable for every transition metal. So the green X's are experiments. These three are from Gerd Ceder's group at MIT back in the day. He's currently on the West Coast. This one is from my colleague Corey Love. And you can see that experiment and theory match quite well. You do get the upward trend, but what is this little dip right here? That just comes from electron count and local bonding. So again, here's these transition metals. You can remember the order of them. I've picked out a few of them and then sort of schematically represented the level of the Z state and the bonding anti-bonding. So in vanadium, you have 2 electrons left in this structure. They sit down here in this weak anti-bonding state. All right, if I go over to manganese, I have 4 electrons. They also can all fit down in this triplet, right? You could fit 6 electrons here. There's 4. You can see that it moves down because I'm going rightward in the periodic table. Now I go to cobalt. The lower manifold is full. So when I get to the next element, which is nickel, that electron has to go up here. So now if I were to measure the distance that this is the lithium electron position, if I measure the distance that the electron falls into the D states, it goes down, down, and then back up. And that's exactly the shape that you have here. And it would go right back up again as I continue to fill these states, but they move over here. But those elements are not stable, so we couldn't measure them. So we can understand exactly the sort of quantum mechanical reason that's these electron states for what we see in the measured and calculated voltages. Okay. Another thing we're concerned about, not just the voltage, we can actually make as high voltage batteries as we want, but then we run into other problems. And this is just a slide that I always show because I really like pictures of fire. So some of these problems are solved. Laptops don't really catch on fire anymore. We kind of fixed that with electronics. We don't let them do as deep charge as we used to let them do. In 2013, an entire fleet of Boeing 787s was grounded. We did the post-mortem on these at NRL to try to figure out what went wrong. Teslas are catching on fire, not just in 2016, but there was one more recently, I think this year. For a while, we couldn't take these on planes, and e-cigarettes are still having this problem. And these fires generally, not uniformly, come from cathode, electronic instabilities in the cathode. And I'm going to show you how we can gauge those computationally before they happen. But they also come from uncontrolled growth on the anode. And this is a little picture of this really beautiful little thing that will cause a short circuit and kill your battery. I also want to show you, I went to a conference in Telluride last summer, and on the plane, my phone did that, which is exactly the problem that I'm going to talk to you about in a second. Your battery swells, and it's because of materials instabilities. All right. So this is the picture again that I've shown you. Bonding, anti-bonding, you get this triplet state, this doublet state. They're split here. We fill the oxygen states first, then you put electrons in these states. This is a schematic that I've shown you already. You're used to it, you like it, but this is what it really looks like when you calculate it. These are not discrete energy states, they're bands because this is a periodic material. So this is a calculation. This is the sort of thing that density functional theory will show you. And this line is the Fermi energy. Everything below it is filled, everything above it is empty, and you can see that it exactly sort of corresponds to the picture we would have in our head if we just started drawing energy lines. I'm showing you this so that you'll understand my next few slides. This is the logical way to plot a density of states. This is the way we actually always plot it. So you'll be seeing them turned this way. Energy will be on this axis. Energy will be on this axis, and number of states will be on this axis. We can also take this density of states and break it down into what character those states have. Did they come from the cobalt? Did they come from the oxygen? Did they come from the lithium? So here you see those are called partial density of states, These are cobalt states right here. When this was turned up the other way, they corresponded right here to these states that originally came from cobalt. The red ones are oxygen states. Those come from these filled ones right down here. So we can break this down into where the electrons are being taken from or put into by element.
You have a whole bunch of new states. So you have gray is cobalt, orange is oxygen.
No, red is oxygen. I'm sorry, the orange is just total. The orange is total.
Some which are mixtures of oxygen.
Yes, exactly. This is, yeah. So the problem with this is that there is oxygen in here, but the gray is in my plotting program, which I guess I'm terrible at. The gray is sitting in front of the red ones, which would be down here. And the red ones, which make up the majority here, are sitting in front of the gray that would make up the total. Yeah, that's a great question. Okay, whoops, I think I went backwards, I'm sorry. Okay, the partial density of states is a measure of the hybridization of the band. So I showed you those bands, oxygen and cobalt, sort of if they're closer together, they bond and antibond more strongly, and you'll see more oxygen mixed into the cobalt states and more cobalt mixed into the oxygen if they're more strongly hybridized. Okay, now, a stable delithiation in a battery goes like this. This is just formal valency. Lithium is an ion. It's 1+. Your transition metal is 3+, and your O2 always wants to be -4. Oxygen insists on being -2. O2 insists on being -4. Everything sort of follows from that. When you take out a lithium ion and associated electron and send it to the anode, then the metal ion changes to +4, and the O2 stays -4. This is stable delithiation. This is what we imagine our batteries are doing, and chemists will call this metal ion a redox couple. It can be reduced or oxidized. All it does is change valency. All right, and here is a picture of density of states of lithium cobaltate as you are pulling lithium out. So this is lithium cobaltate. Here's the density of states, and now it's not total. Now this really is just cobalt and oxygen. And you can see that the states that are right near the Fermi energy, those are the highest occupied states, are mostly cobalt. Okay? But there is some oxygen mixed in because they're hybridized. Now, if I take out 2/3 of the lithium, I'm pulling electrons out of these states, and they end up here in the empty states. And you can see that the states that are emptied out are mostly cobalt. Some oxygen came too. All right? Now, if I pull out even more electron, you can see that, yeah, I'm pulling it out of cobalt, but I'm actually taking a lot out of oxygen. Nonetheless, most of these states are going to be cobalt, and this is going to be stable because I've changed cobalt from 2+ to 3+. Almost all the states that were filled and are now empty are cobalt-like. This is a good material. Okay. But unstable delithiation is when you take these things, you send them to the anode, and instead of pulling charge off this metal ion, which is perfectly happy being 3+ or 4+ or 2+, you start pulling them off the O2. In other words, you form peroxide or superoxide. And oxygen does not like this. Oxygen wants to be 2-, and when it's not 2-, it will go hunting for a way to become 2-. And here's an example of a material that does exactly that. This is lithium nickelate. You see that the states right here that I'm going to pull electrons out of are already mostly oxygen. When I pull them out, they're mostly oxygen. I pull more lithium out, the electrons that come out are mostly on oxygen. This is an unstable system. Oxygen is going to be very unhappy in this situation. And when oxygen is very unhappy, it will migrate out of the structure, find another unhappy oxygen, and make oxygen gas. That will leak into your battery pouch, and it'll swell like mine did on the plane. If you get enough outgassing into your electrolyte under voltage, you can cause a fire. And this is one of the reasons you're oxidizing the oxygen instead of the transition metal ion. Okay, so can we use these theories to build a better battery? My colleague in Corey and I in chemistry thought we could. And we designed this perfect battery. We are getting ready to be billionaires. You can see there's 2 lithium per every copper. So this has a huge amount of capacity. Copper is heavier than cobalt, so it's going to have a higher voltage. This is an amazing battery material. And Corey made it. He got it in this structure, perfect. We cycled it. He caught the glove box on fire at least 3 times. This was before we figured out about these calculations and oxygen. Later, we went back and calculated it, and sure enough, all of the charge is coming off of the oxygen. And here I actually imaged the charge that comes off of the ions when you pull out an electron. And you see, sure, there's a little bit sitting here on the copper, but these are the oxygen ions. It tore a bunch of charge off of those ions. Now we've got peroxide or superoxide and fire. So instead of using theory to make a better battery, we actually used it to at least understand why our battery failed and maybe prevent ourselves from lighting the glove box on fire even more times. OK, so could we think about this and maybe improve the safety of a battery through maybe choosing a different structure? And this is the structure I'm going to talk about next. This is lithium iron phosphate. I'm just going to quickly go through the bonding process. Let's imagine I just had iron and oxygen, and I let them bond and anti-bond. And because they start off close together in energy, they're going to bond and anti-bond strongly. This is going to be my voltage right here. It's rather small. If instead I put a phosphorus ion in there, it's even closer to the oxygen. That's going to be really strong bonding and anti-bonding. These are going to form phosphate units, a bonding one and an anti-bonding one. Now my transition metal is going to be bonding with a phosphorus unit. And these are very far apart in energy, so that bonding is actually quite weak. That pushes this D state up a little bit. And this is where my voltage would be with this kind of bonding, whereas this was where the voltage was if I just let iron and oxygen alone bond without the interfering phosphorus. So this is called polyanionic bonding because there's two anions, phosphorus and oxygen. This is the structure of one of these systems. And there are many examples of these. I just put M for the transition metal ion because you can use virtually any one you like. And this technique is occasionally so successful that you keep this bonding to a minimum and you can short out your electrolyte by having too high of a voltage material. OK, but if you use this particular combination, lithium iron phosphate, you can make a rather good battery. And this was made into a company by Yet-Ming Chow at MIT, I think probably about 10 years ago. I might have that wrong, though. The company went bankrupt and was parted out, not because this isn't a good material, but because there were scale-up manufacturing problems. The point is that of all of the different transition metals you can put in there, iron is probably the lowest voltage, at least by calculation it is. So people would like to use these other materials, but they don't work. And people didn't really know why. Why does lithium iron phosphate work, but lithium cobalt manganese and nickel phosphate don't work? So we wanted to look into this and see if perhaps it was about some of the intrinsic materials properties. So we wanted to look at the concentration of defects to see if maybe one or another of these were more susceptible to defects, the polaronic formation, and the polaronic mobility. So I'm going to skip the results of the defect concentration part and just move on to the other parts, which are polaronic formation and mobility. And just a brief refresher, a polaron is a localized electron. So here is lithium iron phosphate. We tested it to make sure we wouldn't catch a glove box on fire. As you can see, the iron states right here at the Fermi energy are almost all iron. There's almost no oxygen in it. That's because the oxygen is bonded to the phosphorus instead. When you pull it out, you see here it is, that empty state, all iron. Iron is the green. If I image the charge that was pulled off, it's right here. You see that beautiful D state right around the iron. There's almost nothing on the oxygen. You can cycle this forever, and you'll never have any peroxide formation. OK. But these sharp localized states like this that cause these really nice localized orbitals are polarons. They're not band-like conductions. These are broad bands. This is like if you dope a semiconductor, you might be able to get electrons move through it. This is more like that kind of conduction. These are very localized and sharp. You're not going to get much conduction. We call it polaronic. We call it, I'm not sure why it's called polaronic. I guess because it's polarized and people like to use the ON at the end of words. So small polarons are something that is trapped by its own charge field. So imagine that I have an iron atom here, and I pull an electron off of it. Now, this is more positively charged. The negatively charged oxygen like it, and they suck in around it, and they trap that charge right there. Because if this charge were to hop over to the next site, it would have to drag this distortion along with it. So this charge is sort of dressed by the lattice distortion. And when it tries to move through the lattice, it's going to have to pull that along with it. And this is not an efficient method of getting electrons through a material. Okay. Also, and this is for the computational people in the audience, these narrow bands or localized electrons, can't be dealt with the standard computational methodology, which is called LDA or GGA. We have to treat it with a more sophisticated computational method. And I'm going to show you the different methods that we use without explaining them, because I'm going to compare them to experiment. So even those of you who aren't familiar with them will be able to see which ones are better. So first, let me show you, if we were to calculate these, let me see if I have some words here. If we were to calculate these with one kind of methodology called GGA plus U, what happens is you get a delocalized whole state. So this is the dangerous condition I was showing you before. So with this calculation, you see the total density of states in black, and you see cobalt up and down. This is an antiferromagnetic material in orange and green. So anything that's not orange and green is oxygen. All right? And I told you before that's very dangerous. In this material, if I start pulling electrons out of these states, they're mainly oxygen. When I do and image it, it looks like this. All that delocalized blue charge density you see throughout that cell is sitting on oxygens. All right? So this is the sort of thing that we would expect to explode. However, if I use a different methodology, this is a hybrid functional called HSCO6, then you see that I get localized states right here at the Fermi energy. If I pull an electron out of one of those, you can see it's almost entirely green or orange. That's coming off of cobalt. If I image the charge that I pull off, you see it localizes right down there. There's only one, maybe two different places that charge comes from, and they're both cobalt. No charge is coming off any oxygen. We don't have to worry about peroxide formation. Okay, fine. So this is one of those situations in computational work where you can always get what you want. And that's actually a bad thing, because we don't know which one of these is right. Is this a battery material that's going to explode, or is this a nice, safe battery material that we can cycle 1,000,000 times? And in order to find out, we have to compare to experiment. So we did, and I'm just going to put these all up. We did this for all of these three types of different transition metal phosphates that we're trying to distinguish from each other in terms of which ones work and which ones don't. And what you see in the middle is experiment. This is valence band spectroscopy. This is the Fermi energy right here at 0. This is the method that delocalizes the charge and makes it look like it would be an unstable battery. This is the method that stabilizes the charge and makes it look like it would be safe. And what you see is that for every single one of the transition metals, this black line matches the data quite well. This one's actually really nice. And the red line does not match the data really well. So this is good news in that it indicates that all of these materials are quite stable. It's bad news in that this method, the one that predicts this line, is about an order of magnitude more computationally expensive than the other one. So the good news is materials won't light on fire. Bad news is our calculations are going to take forever for us to get them right. So the origin of the problems with the manganese and cobalt versions of this phosphate are not in the peroxide formation. They must be somewhere else. However, in the nickel one, do I show it here? No. I will show you in a second. So we have to look elsewhere for where these problems are.
I have a question about that slide.
Yeah. You want me to go back?
Yeah.
Okay.
The one with the data.
Yeah.
Oh, okay. You really haven't told us what the data measures, or the signal is in the data.
Yeah.
And could you tell us just a little bit so we know that that signal was specific to the location of the charge? Your argument is you keep track of where the charge moved.
Yes.
Whether it moved off the oxygen, off the metal.
Correct.
Why does this signal keep track of
Yeah, great. So this is a valence band spectroscopy, which checks sort of the number of states at different energy depths. That's what the experiment does.
They measure a signal. What's a signal?
Yeah, so
Optical?
Yes, it's optical. Yes. And so let me back up. It essentially mirrors the density of states. So I'm not familiar with all of the techniques that go into it. It's a spectroscopic technique where you test the number of states at different energy depths of the energy.
So something in an optical signal gives you density of states.
Yes.
And then that's not the same as knowing where.
That's correct.
Which atoms
That's right.
lost electrons.
That's exactly correct. Right. So I skipped a step. So this basically mirrors the density of states. And I already know from my calculations that this density of states comes from the one that's localized. So yes, it's exactly a two-step process.
But this whole methodology of density functional, as far as I know, it's not real Schrodinger equation. And you calculate a density, you could have the wrong density and the right density of states. The wrong physical density in space, which is so critical to your argument that the electrons move from one kind of atom to another. So how do you know where the electrons really are? How do you measure?
So in point of fact, that's exactly the opposite of what is true of density functional theory. So the Hohenberg-Cohen theorem says that there's a one-to-one mapping between the ground state density and the ground state wave functions, your ground state solution to the Schrodinger's equation. There's a one-to-one mapping.
Yeah, but you don't necessarily find it, right? Suppose you have the wrong solution.
Well, okay, so this is done by...
Which has the energy right, but not the position of the electrons right.
So what we're doing is using variational calculus to minimize a functional of the density. So to the extent that we've minimized the functional of the density, the energy corresponds to that. But we're not minimizing the energy. We're minimizing the functional of the density. And that's the thing that the Hohenberg-Cohen theorem tells us is correct.
Something exists, but you don't always know it. Am I right?
You don't always know the functional. So we could be minimizing the wrong functional.
Right.
But we're not getting, we are not getting the density right, but the placement wrong. The density is, to the extent that we're getting the density right, we know where it comes from. So we have to check that we're getting the density right. So we calculate things based on that density, such as density of states, and compare them to experiment. This is exactly the point of involving yourself with experimentalists. You have to check your methodology. And that's the point of this entire paper that we wrote, is to say, is density functional theory getting this right? Because we can get it wrong. Not for precisely the reason you're suggesting, but also the methodology isn't perfect, so you check it. Now, given that we are getting it right, at least with respect to the density of states, which matches really well, we can back out from this. So this is a derived quantity from the ground state density, as is the placement of the electronic charge that was removed. They're both just post-processing of the same wave functions that we got out of solving the Schrodinger equation. So if this is right, then my analysis of where the charge is also right. Okay. Now, if it's not that this is forming these extended peroxide networks that make this battery dangerous, then why do some of these materials work and why don't some of these materials work? And our next idea was that some of these that form polarons, and we just showed that they all do form localized polarons and not extended networks of charge, might move through the system faster than others. So this is iron. I've already shown you this. It's maybe in a little bit different format, but there's that localized charge right around an iron. There's an octahedra of oxygen around it, which have very little charge on them. And these are the schematics of the energy states that the electron is coming in and out of. Now it's spin polarized. So there's those 3 weak antibonding states with the majority spin. These are the strong antibonding states. These are all filled. This is a high spin system. This is the electron that you'll be moving in and out to form that polaron. So in the charged system, in the discharged system, there's an electron here. When you're charging, you pull it out. Okay? This is a weak antibonding state. Weak antibonding means there's no real tendency for it to bond or to not bond. So I can pull the electron in and out of that state, and the oxygens don't really breathe in and out very much because it's only weakly antibonding. If you look at manganese, on the other hand, the electron that you're pulling in and out of comes right out of this strong antibonding manifold. And you can see that when you pull an electron out, some of it comes from the manganese, but look how much is around the oxygens. You're pulling tons of charge off of oxygens as well. Not enough to make it unstable, not enough to form peroxide, but enough that when you pull charge off of this, those oxygens feel it, and they suck in towards that cobalt atom. Manganese. Cobalt is somewhere in between. It's got another electron up here, so you've got 2 out of 3 of these weak antibonding states. So maybe you get, by virtue of having 2 of them, you get a little bit stronger polaron And then in nickel, this is the one that I should have put on the other slide, this one actually does delocalize no matter which kind of density functional theory we use. So we've thrown this, this compound out entirely as being too dangerous to actually work in a battery. Okay, these are the average distance changes between the transition metal and the oxygen with and without that electron. So this is sort of the polaronic contraction. And you can see in manganese oxide, it's huge. In iron oxide, it's half. And in cobalt oxide, it's even less. Okay? But we can actually measure this. We can make this polaron on one site and then hop it to another site and see how much energy that takes. And this one is lithium iron phosphate. So we can just hop that polaron to this site, hop it back, and measure the energy at each of those steps. And we can make this curve. The highest energy in this curve is the migration barrier. And this is just your typical transition state theory that says that your conduction is going to go like the exponential of that activation barrier. All right, and what you can see, lithium iron phosphate, here it is. It's the lowest one. This is the battery material that works really well. Lithium manganese phosphate, this is the one that has a lot of oxygen breathing. This polaron will not hop from site to site, and cobalt is somewhere in between. All right, so what does this tell us? It tells us that lithium manganese phosphate is never going to work. There's nothing you can do to this material to make it work. That barrier is far too high. It's way above iron, and it's activated, meaning it's the exponential of that difference. All right, lithium iron phosphate works. We already know that. Lithium cobalt phosphate doesn't look like it should be too bad. It's not really that much higher than iron. So maybe something else is happening to make that material bad. So after we did this research, actually my colleagues at the Army Research Lab started working on lithium cobalt phosphate. And in fact, they did get it to work. And you can make a battery material out of this. As far as I know, no one has ever made one out of this. And we think the reason is intrinsic to the material. OK, now imagine that the problem is hopping from site to site. The lithium cobaltate, even though it does work, it's not as good as the iron. One thing you can do is make the hopping paths shorter. You can grind these things down to nanoscale. So if it's hard for that electron to hop once, of course it's going to be really hard for it to hop 8 times to get out of the material. But if you take it down to the nanoscale, maybe it only needs to make a couple hops before it gets out into the electrolyte or to the current collector. The first battery picture I showed you was sort of a sleight of hand. It made it look like we made batteries out of single crystals and solid electrolytes. We absolutely don't. What we have is chunks of battery material. We mix them up with carbon to make them as conductive as possible. And then we flood both sides with an electrolyte, and we put a separator in the middle and hope they don't touch each other. All right, so it's really a mess. You put these all, and this is actually what your graphite anode looks like, and this is what your lithium cobaltate anode looks like. They're really not at all like the pretty pictures we normally draw. The problems with this are that when you grind them down to nanoscale, you have an extraordinary amount of surface. Nanoscale materials are mostly surface. They're swimming in electrolyte, and they're under the influence of voltage. So this is what our battery materials often start looking like. They're beautiful. And then after we cycle them a few times, gunk builds up on the outside. And this gunk is generally non-conductive to both ions and electrons. So your battery doesn't work after a few cycles because of this interaction with the organics in the electrolyte. Another thing that can happen, I already showed you this picture. I'm actually really proud of it, even though I had nothing to do with it. This is an old SEM picture from Stan Whittingham's group in 1998, showing dendrite growth coming off a graphite anode. This is Corey's optical camera that he built. This is literally a camera picture of the same sort of thing happening on graphite. These little guys will grow across, short circuit your battery, and then that short circuit that's made by lithium metal will heat up, and that can also cause fires. So these are fun, and I'll show you a movie of one later that's even more fun, but they're really dangerous. Okay, so what's a solution to this problem of all this surface area? What if we took our nanoscale particles, I just drew them as weird shapes here, and we coated them with something that's inert in the electrolyte to protect the surface from both that gunk or SEI that grows up and from dendrites? That would keep the material from degrading. And we can do this with ALD. This is not a battery electrode. This is just an example of all different things that we coated with ALD to show that you can make a conformal coating. We even managed to make a crystalline ALD coating, which is highly unusual. So we decided we were going to take our battery materials, we're going to coat them with Al2O3. We know that it's inert in the electrolyte, and it has a nice conformal smooth surface. So this should make our battery materials safe, even if they're at the nanoscale. Okay, but there's a problem with this, and that's that you coat these materials, you put them in contact with the current collector. There's the counter electrode. Now your lithium ions and electrons have to go not just through your material, which may have its own intrinsic instabilities, but it has to get through this alumina too. Okay? And alumina is a terrible ionic conductor and an even worse electronic conductor. So now we've taken battery materials that are fine, we've taken them down to nanoscale, and we've coated them with something that doesn't work as a battery at all. So these are just hard numbers if you would like them. The activation energy of lithium ions is between 0.73 and 1.2. The band gap of alumina is between 5.8 and 7.2. Remember that your battery voltage is about 4.2, so you're never going to get any electrons to go anywhere without short-circuiting your battery with that kind of electronic conductivity. For reference, lithium iron phosphate, which is considered, this is the ionic conductivity, which is considered to be a fairly poor ionic conductor, has an activation energy of 0.25 eV. So you can see that's a minimum of 3 times lower than what we would get from alumina, and it has a band gap of about 2.4. So this material is considered bad, and it's far better than this alumina that we're trying to get to work. So essentially, this isn't going to work, but it does. So these are copper plates with little nano pits drilled in them and filled with silicon. So silicon is an anode material. And in this case, we made all of these, and we did not coat them with alumina. And in this case, we made them all, and we did coat them with alumina. So this is before we've done anything. This is the open circuit potential. We imaged these with an atomic force microscope. This is when we put the lithium in. So when you put lithium into silicon, it swells up. So you can see that the silicon sort of came up out of these little pits. We take the lithium out, they swell back down. After 10 times, when we take the lithium out, the lithium's not coming out anymore. You can see these aren't even pits anymore. These are little pillars. All right? And there's a lot of weird growth out here. That's the SEI gunk that builds up on these materials. All right, but when we coat it with 3 nanometers of Al2O3, that's not supposed to be a 3, it's supposed to be a 5, I'm sorry. 5 nanometers of Al2O3, you see that even after the 10th delithiation, these return to pits. That means all of the lithium is getting in and out of this material even after 10 lithiations. Okay, and if anyone's used to looking at battery data, this is voltage versus capacity, which is amount of lithium. What you want to see is this to be the same every time around. This one is marching slowly back, meaning every time you're losing capacity. Less and less lithium is getting in and out. You can compare that to the coated one. It's a nice tight curve. You're losing almost no lithium as you cycle this. So coating these materials, even though it shouldn't work, theoretically it doesn't work, experimentally it does work. And so then that inspired me to do some computational work to figure out how in the world this was happening. And the first thing we figured out was that we weren't actually coating these and then putting them on the current collector. We were actually putting them on the current collector and then coating them. We had these little current collectors. We had pits in them. We filled them with silicon, and then we coated it. So that eliminates the problem of the electrons. So we don't have to worry about electronic conductivity. But we still have to worry about ionic conductivity. So this is just showing you, we only coated it on one side. The silicon was in contact with the copper the entire time. Okay. Now, this is, I'm being kind of merciful. When I first started to try to figure out how lithium was getting through these materials, this is alumina, this is a lithium ion. I submitted calculations of lithium atoms, lithium ions in the 4 different types of crystalline alumina and in amorphous material. And I submitted them to our HPC center, and I let them run for a month. And I got the calculations back, and I was really excited to see what differences I would see in all of these. And every single one, if I had made a movie of them all, they look like this. That's a month's worth of calculations. And you can see that lithium ion went nowhere. It sat in its spot and didn't go anywhere, and every single one of my calculations looked like that. Those lithium ions really do not get through this material, yet experimentally they're clearly getting in and out through this coating. Okay, This was done at unreasonably high temperatures. Even for simulations, this is pretty high, and it will not diffuse. Okay, but then I thought, well, you know what? I'm putting 1 lithium into these things. Maybe it's just small statistics. Maybe a month is a long time for me, but it's not a long time for nature if I only have 1 lithium ion. So maybe I should shove more lithium ions in there. And I did. I put 2 in, I put 4 in, I put 8 in. And when I got those calculations back, what I saw, this is a plot of the mean squared distance that the lithium ion traveled as a function of time. And what the important thing about this is that the slope of that line is the diffusivity. Okay? So what you see when I went ahead and just put 1 lithium atom in, that's the black one, nothing happened. You see maybe it moved in and out of its little spot a little bit, and then it flattened out. There's no diffusivity there. When I put in a little bit more, I get more diffusivity. A little bit more, more. And a lot more, I get a lot more. All right? So the diffusivity goes up with the number of lithium ions in there. It's not just statistics. The diffusivity itself goes up. Also, though, after some amount of time, it turns over and flattens out, and there's no more diffusivity. So at first, things are going somewhere, and then later, they're not going anywhere anymore. And actually, if you think about it a little while, it's not that much of a mystery. I just took a cell and shoved a bunch of lithium in without thinking, just in the amorphous system. And you can see this is just a picture of where I accidentally put things in. And there's little regions of high concentration of lithium. After, when the diffusivity stops, they're all spread out almost evenly. So what happened is these lithium diffused, and then they got a certain distance away from each other and stopped diffusing. So this suggests that they want to even out. Maybe even they're repelling each other, or there's some Coulomb repulsion that's allowing the diffusivity to start in these materials. And so I'll show you, we did a little more careful thing. I took 2 lithium ions. There are actually 4, and this is actually not a great movie, but you'll see the point. Nothing happens. These 2, because they're far apart, nothing happens at all. Whereas if they're close together, if you wait a little while, one of them actually escapes all the way out. This one had a surface. So the concentration definitely stimulates the lithium to diffuse through the system. And we also saw this in experiment. So this is some data, again, from Corey, who measured the voltage with respect to the amount of lithium. And this is a coated lithium cobaltate versus an uncoated lithium cobaltate. And what you see is that in the beginning, this is a very typical curve for lithium cobaltate. The coated one, we had to apply a little more voltage, especially at the beginning, to get lithium to come out of the lithium cobaltate. And we think that's because, this is the sort of over potential, if you will. That's because what you have to do is fill up that coating before the lithium will start diffusing. So we had to use this whole 4 volts for a long time to just get lithium into that coating. Once we got enough lithium in that coating that the concentration was at the level that the diffusivity was activated, then it starts going along almost exactly like lithium cobaltate. All right. This is then another nice movie just to show you when we made a surface. We let a lot of lithium in there diffuse, and after a while, you see it comes popping out. This is still a periodic cell, so it pops out of the bottom and then shows up at the top. But I usually make people watch at least 3 or 4 boring movies, so I put the nice one in so you can actually see that something does happen when you have a high concentration. Okay, and then we went down and looked at this at the microscopic level. I put 1 lithium ion in here at a site and then hopped it to the next site, just like I did with the Polarons, but this time with an ion. And this is the barrier that you see. It's about 1.1 volts. That's really quite high. But if I just put another lithium here near the equilibrium distance that I found in my previous calculations and then do the exact same hop, what happens is the first step is even negative. So that means it's being pushed through, and the barrier has gone down by half. So when there is more lithium around, that activates the diffusivity. And it's likely because these are lithium ions in this material, and it's a high dielectric material. There's no screening. There's Coulomb repulsion between these things, and they'll push each other apart. And that's why it's important to have a nanoscale coating, because you have to get enough lithium in there to activate that diffusion. And if you have to fill up a really thick thing, you're never going to get it. And in fact, this is bad news for cathodes, because even the amount of lithium that we can get out of a cathode to fill up that coating is going to be too much. That's too much to lose from a typical cathode material like lithium cobaltate. So this is bad news, but we decided to see if we could use it as good news on the anode side where the dendrites grow. So this is, again, this is just a cartoon of how we imagine dendrites growing. You have graphite. You have all these lithium ions out in your electrolyte. They intercalate in until they get right up to LiC6. Any more than this is thermodynamically unfavorable. It won't go in. I still have all these lithium ions out here. The current collector is over here in contact with LiC6, which is a metal, which means that charge can go through to those lithium ions, turn them into lithium atoms, and now it's lithium metal. And they form these little spikes or dendrites at the corners of the graphite, which grow across and short circuit your battery. Okay, but now imagine that we had put an alumina coating on this. Now, until the lithium ions can go through by filling this coating until this is thermodynamically filled, which is LiC6. Now I have a bunch of lithium ions out here, but this definitely does not conduct electrons. So these are never going to become metal. They're going to stay ions out here. And now maybe I won't have any dendrites grow. This isn't really helping me in terms of getting more lithium in. I still hit the thermodynamic limit, but now if I try to push more in, I won't form a dendrite or catch anything on fire. And this was our theory. And now, because I have a few minutes left, I'll show you our movie of how this actually worked. This is, again, that optical camera that Corey built. This is my uncoated graphite anode. This movie starts when it's at LiC6. It's already as full as it can be. And we keep the voltage on and try to pull more lithium in. Yeah, so dendrites grow like crazy. It's really fun to watch. And we have it set to shut off when it hits the counter electrode, which is just off screen. You'll see it stop as soon as it short circuits. There. All right. Now, we again put 5 nanometers of alumina on here. You might think you can see it in this shadow. That's not it. You can't see the alumina. It's only 5 nanometers. All right. And we did the same thing. We overcharged it. Something happens, but it's not dendrite growth. So the good thing about this is that this is a totally safe battery. You can overcharge this. So you can take these batteries anywhere. You don't have to have electronics to keep them from overcharging because you're not going to grow dendrites. We don't know what this stuff is. We're still studying it. Most experimentalists won't let us put something like this that was in a battery and may possibly be coated with lithium metal into their machinery to analyze. So that's still a mystery. That's ongoing research. We don't know if this grew on top of the Al2O3 coating or maybe came through and grew underneath the Al2O3 coating. We don't know. But it provided 100% protection from dendrites, which is really nice in terms of making a battery go.
If you kept going, you sort of feel, you can still see a little bit of gold, yellow.
Oh, a little bit of exposed. Yeah, I think it would just keep going. I think we may have run out of lithium. I don't actually, I know what stopped this. It was the short circuit. I'm not aware of when or why we stopped this. It may have just been set on a timer. But as far as we've done this many times since then, and we've never had anything, just layers of whatever this is plating out. Yeah, we didn't get, if you're asking if we could get dendrites to grow if we kept going, I don't think so. We haven't gotten any to grow. Yeah.
So is this formation, is this reversible?
That's a great question. Yes and no. So it is not fully reversible. Even the dendrites are reversible, by the way, especially if you apply a thermal gradient. So you can actually, so that's one thing we're messing with now is thermal gradients. Not me, because I'm doing everything at temperature equals 0, but Corey is looking at thermal gradients across the battery. And he can reverse the dendrite formation. He can also control the dendrite formation and morphology, make them less spiky and more flat, which is safer by looking at thermal gradients. So yeah, it's reversible, but these are also reversible. In both cases, it's not fully reversible. You're not going to get all of that lithium back onto the metal anode, but you can reverse a substantial amount of it. Yeah. Okay, and I'm definitely out of time, so I'm just going to leave the conclusions up there that you can read for yourself, and I'd be happy to take any questions.
So if it's not completely reversible, what's the sampleability of such a...
So this building this optical cell, I think, was a triumph in and of itself. It does not also have a voltammeter or anything in there. So we can't do the electrochemical measurements at the same time we do the optical ones. So then it's hard for us to know what we're doing because we can't both see and measure. Yeah. Yeah.
So kind of a practical question. If you have an old lithium-ion battery that's not being charged, just sitting around at room temperature, can it spontaneously start swelling up and pop the screen off of an iPhone like the one in my basement?
So I think it can spontaneously start swelling. I don't think unless you're running it, it will catch fire. But yes, it can start swelling, and they do. You can find things sitting in, and particularly if there are pressure or temperature changes. That's what often drives it. I'm not actually the expert on that side of things because I don't work in the applied field. But yes, the materials can definitely, if there are unhappy oxygens in there for any reason, because you overcharged it or because of temperature or whatever, you'll get that outgassing and that swelling. Yeah. Did that happen to you? Yeah.
So, again, this probably isn't in your wheelhouse since you're not the experimentalist, but like when they're making these batteries and testing them, how did they miss the fact that this was going to catch on fire? All the batteries that caught on fire.
Yeah.
How did they
So
not do that?
some of that is. So that's a good question. So not all of these materials that I say are unstable are wildly unstable. They're unstable under certain conditions. So in the end with the Boeing, it was dendrite formation. They were taking some care with the overcharging, but they had packed the batteries in to such a state that the heat dissipation wasn't working. So the dendrites were forming either earlier at a higher or lower voltage than they expected because they weren't controlling for the heat. So some of these instabilities, you can control them, or the materials, as long as you keep the charging rate correctly, you'll be fine. But then, if something goes wrong, then you're not fine. So everyone knows that dendrites grow on graphite. Everyone knows it. You're supposed to correct for it with a voltage profile and with heat dissipation, and they just didn't. So, yeah.
So if you take that 1.5 volt lithium battery from the grocery store, not the fancy rechargeable ones in your cell phone, you irresponsibly open it up with a pair of pliers.
Yeah.
You will unwind it.
Yeah.
And I don't know if this should be on camera. You will unwind it, as far as I can discover a sheet of elemental lithium, because there's a sheet of metal in there, which quickly, as you watch it, starts to oxidize.
Yeah.
It does some very exotic things if you try to set fire to it.
Okay.
I wondered if you had a recommendation, the difference between those kind of batteries, which we're not supposed to play with, but what we do play with.
Yeah.
And then the fancy ones, okay? Can we just throw these things away? Just throw away all this lithium?
So.
And why aren't they rechargeable? And why doesn't the technology, the big batteries, just involve something as simple as sheets of elemental lithium soaked in salt water?
Yeah.
And, why? So really simple things exist. Why is this complicated stuff so hard?
Yeah, so I don't know which part of this question to answer first. Don't do that.
I never did it.
I know. So I would be surprised if I'd be surprised if it was elemental lithium. What you're describing is exactly what elemental lithium does. It sort of just turns black in air. It doesn't catch on fire in air as many people think. Which you can light it. But I don't know of any batteries that actually do employ elemental lithium. And the reason is because the dendrite formation in graphite that I showed you is orders of magnitude lower than dendrite formation in lithium. Lithium just dendrites itself instantly, and there's no way to stop it. There's no voltage or concentration at which elemental lithium doesn't form dendrites. So if you found a battery with elemental lithium in it, I'd be shocked, unless it had a solid electrolyte. Did it?
It's a dirty black stuff.
No, no.
So it's not solid. I mean, you never just have an electrolyte. There's always some lock to it.
When whoever opened this battery opened it, and prior to lighting it on fire, was there a lot of liquid in it or no?
No, it's not a lot of liquid.
Yeah. So this may have been some sort of solid or polymer electrolyte. I don't know. But so you wouldn't have lithium metal in with a liquid electrolyte. And if you don't have it in with a liquid electrolyte, the recharging process in solid electrolytes is extremely slow, to the point that they don't use them.
Yeah.
So that might be the answer to why it isn't rechargeable. Why we don't recycle it is a failure of society. We should be definitely recycling lithium.